Hi, my name is Melissa Micah. I'm with the Hydrologic Engineering Center, and this is Regional Precipitation Frequency Analysis, Part 2, Introduction to Linear Moments. In our regional frequency analyses, especially for precipitation, the statistics of the sample and population are measured in a different way than we typically do for streamflow frequency analyses. In this video, we will explore L moments, which are an alternate way to represent the statistics of a sample or a population. But first, we're going to review product moments. We've seen product moments a couple times already in this class, and they're used to summarize the properties of a sample's central tendency or mean, dispersion or variance, asymmetry or skew, and peak and tail weight or kurtosis. The formulas for the first four product moments are shown here. We won't go over these equations in detail, but I want to focus especially on variance, skew, and kurtosis. Notice how, as each moment gets higher in power, the power of the deviation from the mean gets higher in order as well. So the key takeaway is that product moments accumulate powers of deviation from the mean. We will see shortly that this can lead to problems when using sample moments to estimate population moments. Two studies in 1974 used Monte Carlo to study the properties of product moments and their utility in estimating the population properties of a sample. These studies started with a known population, estimated a random sample using Monte Carlo, and then determined how well that sample represented the known population. The authors found, in their words, the results were unexpected and profoundly disturbing. In a population that had a skew of 5, not a single sample in the run of 100,000 replicates had a skew exceeding 2.67. When these studies raised the skew as high as 15, it merely exacerbated the results. This poses a serious problem. If our goal is to estimate an unknown population from a sample, we need to know that the sample produces a reliable estimation of the population. Because product moments are calculated from powers of the deviation of the mean, they tend to be very sensitive to outliers. Product moments are also algebraically bounded. For example, the variance can never be larger than the square root of the sample size minus 1, no matter what the true variance is. What this means for us is that it potentially introduces bias and error, especially with smaller sample sizes. This is consequential because, as we've seen in other lectures, the population skew is already difficult to estimate from limited sample sizes. An alternative to product moments is something called linear moments, and these tend to be more robust against outliers, they're unbounded, they're nearly unbiased, and they have lower sampling variability of the estimators. All in all, this means these are better for characterizing environmental data where we have moderate or high skews especially. This is a table comparing traditional product moments on the left to linear moments on the right. As you can see, these equations are quite complicated. It's much easier to calculate using software like SSP or programming languages like R or Python. Linear moments are an alternative to product moments that use linear combinations of data. So the key is they do not take higher powers of data in their calculation. As you can see here, we have increasing powers on the deviation from the mean, whereas with the linear moments, only linear combinations are taken. When we use L moments, we typically summarize them into dimensionless quantities called L moment ratios. The first moment we typically keep as is, and this is called the L mean. This is actually equivalent to the traditional product moment mean. The second moment, dispersion, is summarized into a L moment ratio called LCV, which is the coefficient of variance. And this is calculated as the second moment divided by the first moment. Asymmetry is summarized into an L moment called L skew, and this is calculated as the third L moment divided by the second L moment, and we call that T3. Finally, peak and tail weight is summarized into an L moment ratio called L kurtosis, which is estimated from the fourth moment divided by the second moment, and this is known as T4. I will also mention that typical ranges of these values for LCV is from 0 to 1, L skew ranges from -1 to +1, and L kurtosis ranges from -1 to +1. A tool that we typically use in regional frequency analysis to evaluate probability distributions is called the L moment ratio diagram, the LMRD. This is a visual plot of the relationship between L skew on the x-axis and L kurtosis on the y-axis. If you recall, these are the third and the fourth L moment ratios. The way that we read an L moment ratio diagram is by plotting the skewness and their kurtosis on the plot and comparing it to these curves that represent known and common probability distributions. For example, the generalized Pareto, the generalized extreme value in red, and generalized logistic. When you plot a point on the L moment ratio diagram, whichever curve that it falls closest to is the distribution that is best fitting. If you recall from the extreme value theory lecture, the distribution of the maximum of repeated samples of a homogeneous population converge to the generalized extreme value distribution, which is shown here in red. Let's look at an example. Let's say you have a site located in Roanoke, Virginia that has 86 years of precipitation data. You've calculated the L moments for this annual maximum series, which has an L skew of 0.25 and an L kurtosis of 0.16, which is the best distribution. We could plot these on the L moment ratio diagram, which would fall approximately here, where this pink star is. In this case, the best distribution would likely be the generalized normal. To summarize this video on linear moments are a robust alternative to conventional product moments. Many regional analyses use L moments as summary statistics because they're more robust against outliers. The ratios are dimensionless and help us compare information across different sites. The sampling distributions are normal, and they can be used to easily fit distributions to data using the L moment ratio diagram. I also want to point out that homogeneous regions should have similar L moment ratios of extremes. For example, if you have a homogeneous region that represents the same phenomena, the L moment ratios should be very similar for all of the sites within that region. This concludes the video of part 2 for regional precipitation frequency analysis. Please continue on to part 3.